All right, let me go ahead and get started into the core material, and I'll go ahead and turn on presentation mode for at least a few seconds here. This is a presentation that I gave last year at the Global Congress on Process Safety and received the Best Paper Award. So I figured I would do an encore presentation of this, especially considering all of the additional new events that have occurred related to lithium-ion batteries, some of them very well published, others not published. So the name of the paper is Risk Assessment and Safeguarding of Lithium-Ion Battery Containing Facilities. And immediately here, I'll jump out and show you that if this is the paper that was presented was eventually published in Process Safety Progress. So if you have that periodical, you can read the article directly. Otherwise, you can go up to the website and be able to read the paper in a lot more detail. Okay, so beginning, why are we concerned about? So the event that probably caused people to start thinking hard about lithium-ion battery safety was the explosion in the appropriately named Surprise, Arizona. So in Arizona, they were doing a lot of solar. I mean, they have a lot of sun. It's Arizona, so they're putting in a lot of solar panels. And what they were trying to accomplish was to use the solar panels to charge batteries while the sun was shining during the day. And then in the evening, they would then pull the power off of the batteries and put it into the grid. Well, the facility that you're looking at here in the top right of the screen housed all of those lithium-ion batteries. There's a lot of power storage there. Well, this facility was in distress. People saw that there was a lot of smoke coming out of the facility, so they called the first responders. Fire department and hazmat was dispatched. They put a perimeter around the hot zone to try to assess the risk, and they determined that there were elevated CO, so carbon monoxide and hydrogen cyanide, in the area. There were hot spots, and there was a lot of white gas escaping from whatever orifice it could escape from. Eventually, after taking more measurements, they determined that the CO and the HCN were determined to be at a safe level. So 4 first responders decided that they were going to enter the structure and try to deal with the emergency. When they did, there was an explosion, making a long story short. So what you see right here, you can kind of see that the whole outside of this structure kind of bowed, and this thing right here, this is the door that used to be over there where that hole is. So basically, what happened, it's your typical backflash. You've got a very hot set of flammable materials and a deficiency of oxygen. As soon as you open a door or give that material some source of oxygen, it will turn around and explode. And that's what happened. In this case, all of the first responders ended up in the hospital. A couple of them were fairly seriously injured, but luckily in this particular case, there were no fatalities. So this kind of started to grab the attention of a lot of engineers, and people in the community that are responsible for safety, because prior to this, as with anything green energy, there's this halo on it that people will just assume that this was delivered by the unicorns and nothing could possibly ever go wrong. But in reality, anytime you are storing large quantities of energy, it doesn't matter how you store that energy, it is dangerous because there are always mechanisms by which that energy can be instantaneously and accidentally released with catastrophic effect. All right, so introduction. Our energy portfolio is transitioning away from fossil fuels. Politics aside, there's just a reality that says that there are a lot of electric cars on the roads. We're looking at a lot of hydrogen to replace traditional fossil fuels. It's happening. Wind and solar are comprising a growing share. And the problem with wind and solar is that they are not what we would refer to as callable. You can't turn the wind on and off when you need it. You can't turn the sun on and off when you need it. So as a result of these intermittent, non-callable sources of energy, we need to figure out how to safely store massive quantities of energy. And the how we're going to deal with that problem of storage of all of this energy is hotly debated. It's in its infancy. There are people who are pushing electrolysis to make hydrogen. And then there are other people who look at hydrogen and say, well, that's kind of dangerous to store and transport. Let's take those hydrogen molecules and hook them onto nitrogen and deal with ammonia, which is also not the safest thing in the world because it's toxic in addition to being flammable. But we're looking at all the different compromises for how we're going to do this transition. Now, lithium-ion batteries have become a common choice because there's a lot of use and a lot of adoption in microelectronics. Your cell phones, your computers are all using lithium-ion batteries, so there's a lot of infrastructure that's already been created for these devices. So instead of starting from scratch, a lot of people are just trying to take the next step and scale up from the cell phone battery to the car battery to the battery that's going to run your house. Okay, these batteries are sometimes collected into very large systems, municipal scale, which is what we saw with that solar power storage facility. Now, at the end of the day, though, lithium-ion batteries are hazardous. One of the key attributes of a typical lithium-ion battery, and you're going to hear me say that a lot, typical. Right now, virtually every manufacturer has a slightly different recipe for how they're making their batteries. Some are using lithium cobalt, some are using sulfur, some are using iron. So there's a lot of different recipes. So I'm not, in this presentation, I'm speaking to the most traditional common battery configuration, but any particular battery that you're looking at could be different from this prototype in some ways. So for the typical battery, the electrolyte solution, which allows those lithium ions to be mobile, an absolutely essential component of the battery, is a highly reactive chemical. That's going to be ethyl carbonate or methyl carbonate. We'll talk a little bit more about those later. But those chemicals, when they get hot, decompose. And as they decompose, the temperature increases, which causes them to decompose faster. And eventually they could get to the point where they can explosively decompose. So SADT, if you have some time later today, go on Google and search SADT, or self-accelerating decomposition temperature, and you will be treated with all sorts of exciting videos of chemicals exploding when they heat up. Furthermore, there are going to be toxic gases released from the decomposition in the fire. So before you heard that the first responders measured high levels of hydrogen cyanide, but the other chemical that we are more concerned about with is going to be hydrogen fluoride. Hydrogen fluoride is immediately dangerous to life and health at 10 parts per million. So it's a chemical that if we're releasing it, we really want to keep good track of it. Okay, so I said typical, so let's go ahead and take a look at what we mean by a typical lithium ion battery, and I'm gonna work from left to right. So on the left, what's blue here is going to be a big giant sheet of aluminum. That aluminum is going to form one of the two current collectors. So we're going to collect all the electrons that are moving around on these current collector sheets. What we're then going to do is we are going to take the cathode material and smear it onto that sheet of aluminum. Our cathode material here is generally going to be lithium cobalt oxide. There are some numbers here, and I don't remember what the numbers are to make the equation balance, but lithium cobalt oxide, and this material is specifically engineered in kind of, it makes kind of a hexagonal honeycomb, which is really kind of nice because it gives a good place for your lithium ions to kind of sit as they're moving back and forth between the anode and the cathode. So we've got our cathode material, and then we're going to put a a separator between our cathode and our anode. So the reason we need to have, we need to have a separator, otherwise the battery wouldn't work. The electrons would just shoot from one side to the other instead of going through the wire on top where we want it to go. So we need to separate them, and usually we're just going to use a nice long sheet of polypropylene or polyethylene, nice and thin, because remember that these lithium ions need to be able to go back and forth through that separator. So we need some degree of permeability, but not too much permeability. Okay, the other side on the anode, we're going to have, the anode material is going to be graphite. So carbon, sp2 hybridized carbon, pencil lead, however you want to think about it. You're going to have your graphite, and that's going to be combined in some sort of binder to kind of give it a little bit of texture, so that we could take that and smear it on the other current collector over here, which is going to be a big giant sheet of copper. So I'm going to jump out of this presentation and open up another presentation, which kind of gives you some better views of what this looks like. So this is what a typical battery would look like deconstructed. So this is going to be that anode side on the copper current collector. This is going to be the cathode side on the aluminum current connector. You've got this sheet of polypropylene that's sitting in the middle. Now, from a construction perspective, we're simply going to take these three things and roll them up and put them in a can that looks like this guy right here. So this is our traditional 18650 cell, which means it is 18 millimeters in diameter and 65.0 millimeters in length. And it's a little bit bigger than a AA battery. So you're like, well, how can I run my car on something that's a little bit bigger than a AA battery? Well, all that they do is, if you take a look at, for instance, the Tesla Model S, we're going to take over 7,000 of these guys and string them together in things that look like this over here. These are our battery packs. So we're going to put together a bunch of cells into packs and put a bunch of packs together until we can get lots of power at very high voltages. Now this is something that I should know off the top of my head, but I think we're generally running at around 600 volts for your typical electric vehicle. Okay, so that's what the how the battery itself is constructed. Sorry, let me go back right here. Now, the next thing that I'm going to want to talk about is how these batteries fail. And as soon as oh, there we go. Okay, so, pardon me. All right, so how do these batteries fail? I've already mentioned that the biggest item we are concerned about is the self-accelerating decomposition. And that's because the material that is in the electrolyte, actually, let me back up a little bit because I didn't talk about the electrolyte yet. So ultimately, when you're charging a battery, you're taking an electron out of the lithium cobalt oxide and you're sending it over here to sit on the graphite. And then when you're using the battery, you're taking that electron out of the graphite and sending it back into the lithium cobalt oxide. But for every electron that moves this way, we also need one of these lithium ions to move that way too. It has to balance. And in order for these lithium ions to be mobile, they need to be in an electrolyte solution. Now, in the olden days, or even today in a traditional internal combustion engine automobile, we have batteries. And those batteries are of the lead acid construction. And how the electrons move in a lead acid battery is that you have a swimming pool of sulfuric acid that is going to allow the ions to move back and forth relatively easily. Well, for lithium ion batteries, we chose lithium instead of lead to be the material that's moving around. Why did we choose lithium? Real easy. Go ahead, little exercise, pop open your periodic table and find the lightest metal for me. It'll be in the top left corner and you'll see that it's lithium. Okay, so it all has to do with weight. And lithium is going to be the lightest metal there is, and that's what we're using in our phones and in our laptops, because we don't want them to be heavy, yet we want them to be powerful. The problem with lithium is it is not compatible with water. And again, you want to have some fun, go check YouTube and find lithium and water. Search for that and you will find people dropping hunks of lithium into water and watching it explode. So the lithium that is going to be moving around, we need to dissolve it in an electrolyte solvent, and we're going to use ethyl carbonate and methyl carbonate. So let's see if I could do this. The carbonate is a funky molecule. First off, you start with a 5-carbon ring, which right out of the gate you're like, 5 carbons. That guy doesn't want to hang out. And then you've got these double bonded oxygens. You just look at this molecule and say, this guy does not want to stay together. This molecule wants to decompose into that carbon monoxide, this methane, and this ethane. And when you heat it up, boy, does it decompose into that, and in a hurry. But at this point in time, that is the electrolyte solution of choice, so we go with it. But that is kind of the starting point for everything that's going to go wrong in our batteries. So that's the solution, and the electrolyte itself is lithium hexafluorophosphate, LiPoF6, I believe. That's, oh, there it is. LiPF6. So that's kind of where that lithium ion is kind of in that this is in solution of the ethyl carbonate, methyl carbonate, and that's what's allowing your lithium ion to move around. All right, so as I mentioned, we have a lot of issues that are related to uh, what's eventually going to end up being called a thermal runaway. You can initiate a thermal runaway by overcharging it to get it hot. You can also over discharge it. So if you over discharge a battery and the voltage difference gets too low, you're going to cause that the copper of the copper current collector to start to go into solution. So it's going to dissolve into your electrolyte solution. And when you charge the battery back up, that copper is not going to try to go find its home where it came from. It's going to turn back into a solid wherever it was when the voltage came back up. That is going to result in these things called dendrites. So I talked about a copper dendrite, but you can also get a lithium dendrite. So I mentioned when you're charging, you're sending an electron this way, and you're sending one of these lithium ions this way also. Now, the lithium the lithium ions, as I mentioned, are sitting in this kind of honeycomb structure of the lithium cobalt oxide. Well, when you're discharging, that lithium ion is going to come back. But these guys don't have addresses. They don't have name tags. They don't go try to find, their home and go back to it. They just go back to wherever is convenient. And what ends up happening is you start getting a stack of these lithium ions. So instead of everything going back and forming a uniform layer, they start to form dendrites. And when you have a dendrite, what you have is a path of less resistance. So your current is going to want to flow where you have less resistance. So you're going to get preferential flow of your lithium ions in one focused location instead of the flow being distributed across the whole battery. And as you know, I'm assuming that basic electricity, the amount of heat generated by the flow of current is going to be a function of the current squared. So you're going to generate extreme hot spots as a result of these dendrites, and again, as time progresses, they get worse and worse. So all of this could end up resulting in elevated temperatures, or actually, I'll come back to elevated temperatures, but the dendrites are going to eventually result in separator failure. So let me go back to the other presentation, and I'll show you what that separator failure looks like. So this is just looking at a sheet of the separator material, and what you see right here is a pinhole where dendrites or whatever other mechanism caused preferential flow through that spot, and eventually it just ate a hole through, and now I've got one location, one hot spot where I'm going to get a preferential flow through there, and that's going to cause a lot of heating, which then is going to result in a thermal runaway in that particular spot. All right, let's back up to the other mechanism. Now, there are other things that will cause thermal runaways. Elevated external temperature. So just being in proximity to high temperatures is going to cause this runaway reaction. That runaway reaction I showed you before is going to occur at approximately 65 C is going to be your self-accelerating decomposition temperature of a typical lithium ion battery. Once you get to 75 degrees C, this is the NTR, or the temperature of no return, meaning once it gets that hot, it's going to completely decompose and there's nothing you can do to stop it. Now, these temperatures might seem high, but remember, the whole battery doesn't need to be this hot. Only one portion of the battery needs to be hot, and that's what happens when we get the dendrites. It's also going to be what happens when we get this mechanical damage puncture, which I'll talk about in a second. But also, if you have batteries and you're storing them and you're shipping them, these kinds of temperatures are not outside of the realm of possibility. If you have things enclosed, you don't have good cooling mechanisms, you don't have circulation, and let's not forget that the charging and the discharging of the batteries also generates heat. So getting to that temperature, there are a lot of ways to do it. It's surprising how many ways you could get yourself into trouble. And I will kind of give you another case history to do some research on. And this past winter, it wasn't too long ago, there was a cargo ship called the Felicity Ace. So if you want to Google Felicity Ace. Now, we don't know exactly what happened, but one of this ship was carrying a large load of electronic vehicles from Europe to the US. A lot of them were Porsches, which is probably why it got a lot of press. At least one of the cars caught on fire, and I will scream up and down that the press should never call it a fire. It's a self-accelerating decomposition. But basically, once one car got caught on fire, it generated enough heat to cause the self-accelerating decomposition on the next car, to the next car, to the next car, to the next car. Next thing you know, you've got hundreds of electronic vehicles all on fire, all decomposing. And long story short, the Felicity Ace is now at the bottom of the ocean, because once it starts, you cannot stop it. Okay, other items, cooling failure. And so I mentioned how, you can get a failure of the separator. Well, a very good way to get a failure of the separator is just to puncture your battery, and then your cathode and your anode are physically touching each other. You're going to dump all of your energy in one shot, and that's going to cause everything to go. So let me show you what that failure looks like. So I'm going to go back to that other presentation that I had, and hopefully you'll be able to see this video run. I apologize if you can't. So that is what happens when you puncture a lithium-ion battery. I'll hit this one section at a time because there are different stages. So the first thing that happens is when you puncture the battery, you're going to get, all of a sudden, all the energy turns into heat because your anode and cathode are in contact with each other. And if you look closely, you can see like kind of white hot reaction energy occurring. The next stage is what's going to be called the gassing stage. So you're going to see gas coming out. You're going to see the packet swell up, and you can see clear gas coming out. And what's happening here is your organic solvent is decomposing. It's turning from ethylene carbonate into carbon dioxide, carbon monoxide, ethylene, ethane, methane. All flammable gases are being created, and they're shooting out of the container. And they will shoot out of the container because the designers knew this could happen, and they built these batteries with rupture discs that are going to allow you to dump the material out instead of causing a violent explosion inside the cell itself. We're basically going to have an engineered pathway for these gases to escape. The next section in the decomposition now is where you're going to start to see all of this smoke happen. And what happens is, well, everything inside the battery is decomposing. Now we're going to get thermal cracking of that polyethylene, polypropylene film into organic solids and methane, ethane, so on and so forth. And you're also decomposing your lithium cobalt oxide, which is generating oxygen, and you're decomposing your graphite. So a lot of this smoke is going to be longer hydrocarbon chains coming off of the graphite and coming off of the separator. The next step, which may or may not happen, is the ignition and combustion. So the self-accelerating decomposition reaction just generated all kinds of extremely hot flammable material. And well, if I have a whole bunch of extremely hot flammable material, if that mixes with sufficient oxygen, I will get a fire, a flash fire. But if that area is contained, if that area is confined, I very well could instead get a vapor cloud explosion. So that's kind of the nuts and bolts of what's happening when these batteries decompose. And in terms of consequences, you're going to get that intense heat from the rapid discharge. You're going to generate a bunch of gases, including carbon dioxide, carbon monoxide, hydrogen, methane, ethene, ethane, and propane, and a lot of particulates. So a lot of the carbon from the anode is going to kind of just get kicked up as smoke. Now, if that weren't bad enough, remember we were using lithium hexafluorophosphate as our electrolyte. And why are we using fluorine? Once again, pull out your periodic table and you will see that fluorine is going to be our lightest halogen. Again, we're doing everything in our power to make these batteries light. As a result, we're using some of the most dangerous chemicals there are. So, could you effectively do something similar with lithium hexachlorophosphate? Sure, but chlorine weighs dramatically more than fluorine. So that's why we kind of get stuck in our trade-offs with these highly hazardous chemicals, because they have other properties, specifically lightness, that we desire. Now, when we heat up our lithium hexafluorophosphate, we have the ability to create hydrogen fluoride. As I mentioned, immediately dangerous to life and health at 10 parts per million. This falls into the category of what we will call a wildly toxic chemical. But even so, this POF3 is a chemical we don't know a lot about. We don't have a lot of data on because nobody makes it on purpose. And we have every reason to believe that this chemical makes hydrogen fluoride look lazy, look sloppy. This one is, we believe, dramatically more toxic than hydrogen fluoride. Okay. So that's what's going to happen. You're generating gases. Some of them are toxic, and we have the ability for all of this flammable material that we gassed off. If it's confined, if you give it a source of oxygen, we can get a vapor cloud explosion. Now, if this happens to the battery in the phone that's in your pocket, it's going to be unpleasant. You might, get some third-degree burns. You might end up at the hospital to just, kind of get yourself checked out. As a worst-case scenario, typically you're going to, need to buy some new pants. But the big concern though is, well, what happens if I have a lot of these batteries in one location? What hazard have I created for myself now? So in order to safeguard ourselves, there are a lot of things that we can do. We have charge interruption devices. So basically ways to detect that our batteries are overcharging, undercharging, and shut them off. We have these things called positive temperature coefficient devices. So remember, I said that if you start to go to a thermal runaway, you're going to gas off and you're going to kind of expand your the casing of your battery, and then eventually the rupture disk will lift. Well, that positive pressure can actually, I'm sorry, that was my charge. Sorry, that was my charge interruption device works on high pressure. It's going to disconnect your load and your charging device from your battery. Positive temperature coefficient devices are going to work on the separator, in that if the temperature of the separator goes up, it's going to change its chemical characteristics to prevent current from going across the separator. And that's also termed the shutdown separator. We do have those pressure relief devices to prevent the individual cells from exploding. Battery management systems, for lack of a better word, are the safety instrumented systems. They're the controllers that control the charge and discharge of your battery and can detect that your temperatures are getting high, your resistance is getting high, various other ways to basically just shut down the charging and discharging process. Also, for your facilities, you will be potentially looking at traditional fire protection equipment if the lithium ion battery runaway occurs in your facility. So dry chemical systems to prevent a fire from occurring once you know that the conditions for the self-accelerating decomposition have occurred. And also, we're going to want to leverage a lot of gas detection to know that the runaways are occurring, take safety actions to either vent the facility or prevent oxygen from getting into the facility, and also to warn people of the hazard and prevent them from walking into a dangerous situation, potentially, for instance, a large hydrogen fluoride vapor cloud. So when you're looking at a facility that contains a lot of lithium ion batteries, let's say, I don't know, a cargo ship that's carrying a few hundred electronic vehicles. You're going to want to do an assessment of the risk on that overall facility. So you will start out, as you always do, with a process hazards analysis, a PHA. The methodology that we would most commonly use would be the failure modes and effects analysis. You've got other choices, checklist, HAZOP, so on. But with battery systems, we typically know what the failure modes are. So, excuse me, in a facilitated study, we would just inject those failure modes and see what the effects are, what the consequences are, and make sure that we have the appropriate level of safeguarding. The other thing that's different about a PHA for this type of system is you really want to note the knock-on effects. So for the Felicity ACE, if you look at one cell and you look at, well, self-accelerating decomposition is going to cause the battery to overpressure, it's going to pop, it's going to relieve. That's bad, but that's no big deal. Well, when that first cell causes the second cell to run away, which causes the third cell to run away, which causes a massive fire, which heats up the battery in the car next door, which heats up in the battery in the car next door, and now our ship is on the bottom of the ocean. We really need to think about knock-on effects, and we need to think about if one battery pack, if one cell goes into runaway, what do we do? If one battery pack goes into runaway, what do we do? If one system of battery packs goes into runaway, what do we do? Because ultimately, this is not a traditional fire. You cannot put this out. There's another great article about an electric vehicle vendor who had a car that was on fire. So they literally took a crane and put it into a container that was filled with water. And this car continued to burn. I don't know if you see me doing my air quotes. It continued to burn completely submerged underwater for 5 days. So what you need to think about is, how do I get this battery system that's undergoing a self-accelerating decomposition, how do I get it away from everything else and let that self-accelerating decomposition go to completion? Because you're not putting it out. Okay, so that kind of leads us into the locations, spacing, and facility siting being really key to this effort. And then also, so in addition to facility siting, we're going to want to do some gas detection mapping. So you're going to want gas detection, combustible gases, hydrogen fluoride, again, depending on what your specific composition or your specific battery is. But we would want to run some dispersion modeling to figure out where to put detectors. So what you're looking at up top here is a computational fluid dynamics model of a runaway of a battery system in a single electric vehicle. So this, what this box is it's a test cell where some company is testing some attribute of this electric vehicle. And we ran dispersion models to figure out, in a plausible worst case scenario, how much hydrogen fluoride could this battery kick out. And then the cloud that you see in green is the extents of 10 parts per million. So basically, if you're inside that green cloud, you have been exposed to an immediately dangerous to life or health dose of hydrogen fluoride as a result of that scenario. So what this modeling also tells us is, when the gas cloud occurs, where is it going to go? And that is going to help us to lay out the gas detector. So is the gas going to be dense and hug the ground? Is it going to go up? How does the HVAC system impact where that gas cloud is going to go? So we can have a very high degree of confidence that when a gassing event occurs, we're going to detect it. We're going to go into alarm to be able to take our next step of mitigation measures for that emergency scenario. Okay, so in terms of fire and gas, fire suppression and gas detection, an objective would be to extinguish a flame and cool. Now, I kind of emphasize the fact that you can't put the fire out. I should be a little bit more precise on that. The flammable materials that came off, your carbon monoxide, methane, those will burn. You can put those fires out. But the decomposition reaction will only stop if you can cool the battery, not the outside of the battery, the inside of the battery. You have to be able to cool the inside of the battery back down below the self-accelerating decomposition temperature. So your dry chemicals are not going to provide the cooling that are going to be required to be able to stop that decomposition reaction. Coolants are generally not practical or suitable. Trying to cool this down with water, trying to cool it down with liquid carbon dioxide is one of the items that has been bandied about. Don't use liquid nitrogen, because your liquid nitrogen will react with your lithium and basically make things worse. So in general, containment is often the only feasible mitigation. So just get everything away from it, isolate it, and let it go to completion. Okay, so for our fire suppression and gas detection, we need to be focusing on limiting the amount of material that gets built up. And in this case, you might want to take a different mental approach to say that ventilation might take precedent over fire suppression because we've got a toxic gas and the combustion reaction might be a lower risk than accumulation of hydrogen fluoride. So these are all things that need to be worked out during the risk analysis process. Ultimately, what Felicity ACE did not do is prevent cascading thermal runaways. So NFPA 855 has some information on this. They recommend a 3-foot spacing between battery groups and walls. That's good guidance initially, to be honest. We have a lot more research to do, and I have a feeling that that spacing is going to, sometime in the future, be a function of the total chargeable quantity of the battery. So how much battery material are you going to have is going to determine what that spacing needs to be, because I think that for Felicity ACE, that spacing might have actually been achieved, and it still, the thing still went. So those are some of the considerations on the fire suppression side and the gas detection side. All right, so conclusions before I turn the floor open to some Q&A. Lithium-ion batteries are generally robust. Okay, I don't want to make it seem like, you know, lithium-ion batteries are the end of the world. The probability, the frequency of these failures is relatively low, but don't let that lull you into a sense of complacency. You still need to analyze it. You still need to safeguard against it. Our biggest key here is being able to provide sufficient spacing and also have emergency response mechanisms to create spacing to be able to pull that vehicle out. Matter of fact, this is very interesting. I saw an article on LinkedIn yesterday that I really need to do a little bit more research on, but apparently I think it was in either the UK or Germany, an electrical vehicle went into a self-accelerating decomposition. Of course, they called it a fire because everybody calls it a fire, but self-accelerating decomposition, and that heat caused loss of power to all of the vehicle's subsystems, one of those subsystems being the emergency brakes. And the emergency brakes fail to release, which makes sense because you don't want your emergency brake to fail to the closed position while you're going down the road at 80 miles an hour. So there's less danger in having a parked car release than having a moving car go into braking. But when it did, the car kind of rolled backwards into another car and caught that car on fire too. So the ability to, once the situation is started, to be able to remediate it by moving the battery, moving whatever is containing the battery, that's something we need to do a lot more work and research on. We also going to want to look at appropriate gas detection. Flammable is going to tell us that we're running into a bad situation, and in some cases, some chemistries are going to result in large quantities of very toxic materials, and we need to address those hazards. Adequate ventilation is hopefully going to allow us to prevent accumulation, and we would definitely recommend studying the airflow in the rooms that are containing these lithium-ion batteries and look at typical gassing scenarios to make sure that we're never going to develop enough gas in the room to allow a vapor cloud explosion to occur, like what happened in Surprise, Arizona, that we started our discussion with. And also, we might want to consider explosion prevention and deflagration venting on the facilities themselves. So in our first example in Surprise, Arizona, it turned out that the door kind of worked like a de facto deflagration vent, but we might want to look at having our shipping containers actually elegantly be able to vent some of these deflagrations with kind of minimizing the amount of knock-on effects. All right, so I will open the floor up to questions, and yeah, I did that presentation in 15 minutes at CCPS, so I'm almost at an hour right now. So hopefully you found that information to be useful.
Yeah, anybody who has any questions, go ahead and turn your mics on. You should be able to turn your own mic on.
Ed, have you looked at what specific gases would come out of the batteries before you have a runaway so that you can detect it early?
Well, the problem is that it's the runaway that's causing the gassing. So, and I guess I should be a little bit back up a little bit. If you have gassing before it goes into a full runaway, what's going to happen is you're going to see your battery start to swell. So kind of a preemptive or a precursor could be to look at mechanical stresses on the container of the lithium ion battery itself. So I'm sure a lot of you are familiar with, seeing people's cell phones or laptops where the battery kind of swelled up and the device is all misshapen. Well, what's happened is that cracking reaction of the electrolyte has already occurred, but it hasn't escaped the pack yet. The pressure hasn't gotten high enough to pop the relief valve. And for gas detection, the gas detection won't kick in until you've gassed so much that you've popped the relief valves on your cells. And at that point in time, you're in damage mitigation mode as opposed to more of a proactive prevention mode. But now that you mention it, I'd never thought of it. Looking at the mechanical stress somehow in the battery cells themselves could be a great leading indicator that some of these battery pack manufacturers might want to look into.
Ed, if I'm not mistaken, wasn't that something the Purdue Process Safety Center was considering too?
Purdue Process Safety Assurance Center is looking at spectroscopy in the battery. So basically, you can use spectroscopy to try to determine the internal resistance in the battery. And like a resistance temperature device, you can correlate the resistance internal to the battery to the temperature of the battery. So that would be kind of an attempt to measure the internal temperature of the battery by using spectroscopy. That's kind of one of the big research areas at Purdue. Nitin, I think you were next.
Yeah, thanks, Edward, for a very nice presentation. Really, you have given quite insight of what lithium-ion battery is. I just wanted to know because I have seen a couple of car carriers, and I think presumably when the fire occurred, both these vessels gone into the seabed straight away. And I could see that this means the potential of the lithium is getting in contact with marine water. And all these vessels which are coming up, and we could see a lot of trend of the hybrid vessels where these lithium ions or batteries are getting popular. What will be your advice to the designers who are designing these vessels?
Yeah, so in terms of damage to the consequences of the failure mode of the battery packs being submerged in water, I am going to have to step back a little bit and say I have not researched that yet. But now that you brought it up, it is an interesting concept that, I mean, we do have lithium. Now, the lithium is not free lithium. You've got lithium hexafluorophosphate in your electrolyte. You've got lithium cobalt oxide in your cathode. So it's not going to have that same reaction as if it were just a pure elemental lithium exposed to water. That would be really bad. But the other thing is the individual cells are basically effectively sealed pressure vessels. So that the water shouldn't be able to get into the battery cell. So I don't think submersion of these cells in water is going to be a failure mode that jumps out at me as being incredibly important. But I will tell you right out of the gate, I have not done any research on it either.
Mm-hmm. Yeah. Thank
All right.
you.
Okay. Brandy.
Yeah.
Hi, Ed.
Hi.
So I have a question about battery electric vehicles, and maybe you know it, maybe you don't, but they have a battery management system on board. Do you know anything? Is there a warning system that comes online on a vehicle that tells you that a car's battery is having issues and shuts it down, or do you know if there's any type of mechanism like that?
I do not, and I have to tell you, my knowledge of vehicle, of actually being an end user of electrical vehicles is very limited. I am still on the internal combustion engine train. Again, not that I have any problem with electric vehicles, it's just that I haven't gotten there yet. Probably because I'm cheap. My car just crossed over 100,000 miles this morning, so I don't go through them really quickly. But the vehicles that I have had experience with did not have anything other than just kind of a light, a check battery light, common trouble alarm.
Okay.
And I don't know, to the typical vehicle driver. For them to, get, a warning that cell 5 of battery pack 7 is an excessive temperature, I don't know what they're going to do with that. So I don't even know if for the end user, having more detailed information than a common trouble alarm would provide them anything they could use.
Right. Well, we're at Umicore. I think you guys actually came and helped us out.
Absolutely. I was
so
there.
Like for us, that would be a huge thing, getting that, hey, there's a battery trouble. Well, then we're going to get the car out of the facility, right? So
yes.
But obviously we haven't had a thermal runaway here, so I don't know what the warning alert's going to be.
Yeah, exactly. But what I think that the vendors should be doing, the same way that I can't diagnose what's wrong with my car, if I take it into a shop, they can plug in their diagnostic tool and get a whole lot of information that I, the end user, can't have.
Right.
So I would expect that the electrical vehicle manufacturers should be able to give you, any certified maintenance technician, an entire raft of diagnostics should be available. And if they're not, shame on them. And we need to talk to some people to make that happen.
Right.
As far as I know, the car makers, they individually isolate batteries that are not going well with the voltage and all that, and keep the rest running. That's why the effective efficiency of these battery packs over time will go down, because they will shut down certain cells.
That's interesting. Okay.
No,
Yeah,
absolutely.
My daughter drove an earlier generation of Toyota Prius, and the dashboard actually, it had an intelligent dashboard that told you how the process was working and if anything needed attention. It's not as detailed as the geeks like us would like to have, but it does give you an idea of the overall health of the system, and there is some warning that the system may be malfunctioning, but it wasn't. It's like red lights on the dashboard. It really doesn't mean much, unfortunately.
Okay. Good to know. Thanks, guys.
Uh-huh.
Nice to hear from you, Marcio.
we're already 3 minutes over, but if anyone has any last questions, you're saving me from having to go to an ISA committee meeting. Jim.
Hi, Ed.
Hey.
We have been working with a manufacturer of a sensor for gas detection, and through some algorithms and different things, they've found ways to get a very early response on the beginning of a thermal runaway situation when the solvents are first released, and subsequently have been informing us that if we catch it at this point, we can shut off the charge if charging is the method of abuse, and which is the only one we can control. That we could shut that charging process off and potentially prevent thermal runaway, the battery from going to thermal runaway. Have you had any experience or any discussions along those lines?
Okay. Well, okay. So from a pure gas detection perspective, there are a lot of different ways to detect this gas. It contains a lot of methane, so your traditional IR type detection will be able to pick this up. Everything is combustible. So assuming you have enough air, your catalytic bead type detector should be able to pick this up. Your laser type detectors, there are a lot of different ways to detect that this is occurring. So, mechanisms, I think we've got a lot of background in how to detect the releases when they occur. The big question then is what do you do about it? And if you can again, if you can detect that one of your cells is gassed off, the hope would be that the battery management system would be able to stop the charging process. And again, that's only if the abuse is a result of charging. Now, what stopping the charging wouldn't do is, well, the cell that gassed off is hot. It's very hot. So we're just going to get conduction, convection from one cell to the next cell if they're not well insulated. And generally, they're not going to be well insulated because they are heating all the time. So we've got a constant problem of trying to keep these cells cool because charging them heats them up and discharging them heats them up. And that basically kind of precludes you wanting to put a bunch of insulation around them because you're robbing Peter to pay Paul. From a risk perspective there. Yeah, I'm seeing a lot of research on different technologies to be able to detect that the off gassing has occurred. But to be honest, I don't see that as being the issue. I see the issue being once you know it's gassing, what do I do now? And the quicker you can detect it, the lower the probability of those long-range knock-on effects where this cell triggers that cell, triggers that cell, triggers that cell. What I would be really interested in, and this is something that kind of more goes to a battery pack manufacturer perspective, is there a possible way to kind of use a more robust engineered cooling system to possibly flood the cooling system with like a liquid carbon dioxide to just basically subcool everything real fast. But that's all in early research stages. Okay, well, Jim, I'm going to go ahead and say that thank you to everyone for your time. And I've already gone about 10 minutes over what you promised to give me. Thank you very much for your time. And I'll let Jim wrap it up.
All right, thanks everybody. In about a week, I'll actually have this posted up as a recorded webinar on the site. If you want to go to, if you want some friends to see it, you'll be able to point them to it. It may be shorter than a week, but I'll send a notice out in about a week to everybody, okay? All right, thank you very much for your time. And as always, we do these about once a month, pretty consistently, and we will have an exciting topic for next month here shortly. Take care. Bye-bye.
Thank you,
Thanks,
Ed.
everyone.
Thank you.